we will continue our lectures on process control. In the last class, we talked about how to model a process. I talked about writing conservation equations, phenomenological models, defining variables, writing these equations for control volumes and so on. In this lecture, what I am going to do is I am going to show you the same model in a form that is called state space modeling. Typically, undergrad control classes do not talk about state space modeling. However, it is a very simple extension to the standard equations that we showed last time, and it is a very useful framework when we start doing multivariate process control or multivariable process control. So, it is important to understand state space modeling, and the way I am going to do these lectures is I showed you the first principles modeling last time. I am going to show you the same thing in state space, and I am going to show you how you solve these state space models in time domain, get some results, and then show you how you can solve the same problem in frequency domain. We will introduce Laplace transforms at the time, and then I will show you the connection between solving these equations in time domain and frequency domain or using Laplace transforms. So, ultimately at the end of this series of lectures, you would have understood Laplace transform, and you would also know that Laplace transforms is not some general mathematical abstraction, but it is basically representing fundamental physical process. The only thing, as I mentioned in the last lecture, is that while most fundamental physical processes are nonlinear by nature, the use of Laplace transforms is largely for linear systems. So, you have to take this additional step of linearization of the model. So, you have a first principles model, which itself is a conceptualization of a process, and there will be some errors in the conceptualization. It will turn out that these models are nonlinear. However, we want to work with linear models because it makes the theory and implementation easier. So, we linearize the nonlinear model to a linear model. So, there is the next level of approximation there, and once we linearize, we get a transfer function model, which we will see after we see Laplace transforms, and you have to understand that this transfer function model is a representation of the true process, albeit with approximation. So, the quality of the model will depend on how approximate these models are in terms of what is the impact of linearization and what is the impact of the errors that we might have made in our conceptualization and so on. So, you have to remember that while these models are very useful in control, they are still approximate. Now, with this preamble, let us go back to the previous lecture that we saw in this course, which was simple liquid level system model, and from last time we did see this. You write this conservation equation, mass conservation equation for the control volume of liquid in the tank, and then you use this phenomenological model to come up with consolidated model here. And we said that if you wanted the behavior of this process at steady state, then you have to set dH by dt equal to 0, which will give you this equation. This flow inlet at steady state is r times root of height at steady state. Then we said because of this term right here, this is a nonlinear model. So, we linearize this, and we linearize using Taylor series approximation, and if we linearize this root of h, we take up to the first term, which is what gives you this term here. And I also said anytime you linearize, you have to evaluate that function at an operating point, and the operating point that we choose is this HSS. So, that is the operating point around which we are linearizing, which you can see here, h minus HSS. Remember from your high school, whenever you do a Taylor series approximation, you will have f of x0 plus f prime evaluated at x0, x minus x0. This is a term like that. So, after all of this algebra is done, when you put all of this in terms of deviation variables, this is the form that you get here. The hat basically symbolizes that at t equal to 0, this h hat is 0, simply because we start from a steady state. So, this equation has been derived assuming we start from a steady state. The actual value of h is HSS and the actual value of Fi is FISS, but because we define h hat as h minus HSS at time t equal to 0, if h were in steady state, then this would also be HSS. So, h hat will be 0. So, that is what we have written here, h hat is 0, Fi hat is 0. So, look at this equation, this is the form of the equation that we are going to use quite a bit as we go forward. So, this is something that we saw in the last lecture, and this is a recap of this, and I wanted to get to this equation because the notion of our state space model starts from here. So, in general, a state space representation is written in this form: x dot equals ax plus bu, y equals cx plus du. Here x is what we call as a state variable, y is the measurement or output variable, and u is the input or manipulated variable. So, we in an undergrad course we call this the manipulated variable. Now, typically this is written in the vector form. So, you could have x with a dimension of n by 1, that means there are n states, and you could say, so x is n by 1, you could say the output variables are, let us say, p in number. So, this will be p by 1, and the input variables are, let us say, m in number. So, this could be m by 1. So, this is a general vector form of the state space representation. We will get back to this when we talk about multivariable control, but since I am introducing state space representation for the first time, I thought I will do the general form and then quickly move on to this simple liquid level tank example that we see, and then tell you how all of this figures out in this tank example. Now, if x is n by 1, x dot is also n by 1. So, this is the derivative of the n states. So, this is n by 1. So, this A matrix has to be n by n, only then you can do the matrix multiplication. And similarly, because u is m by 1, there are m inputs, this B matrix has to be n by m, so that this matrix multiplication can be done. Now, since y is p by 1, this C matrix has to be p by n because x is n by 1. So, this multiplication can be done, and similarly this D matrix has to be p by m and u is m by 1, so that you can do the matrix multiplication. So, this is the general scheme. Now, if n is 1, p is 1, m is 1, then I have only one state, I have only one output variable, and I have only one input variable. Notice an interesting thing here, when we talk about seesaw control, we talk about actually one input and one output is what we talk about. So, that basically means m is 1 because we said there are m inputs, and p equal to 1 because we said there are p outputs. Now, n can be anything. So, n can be 5, 10, 1, 3, whatever it is. So, these are not dependent on each other, right. So, you could have a system where you have 5 states, but only one input and one output. So, the key takeaway from this, though it is not relevant right at this point, it will become relevant later, is that you could have a seesaw system which is single input single output system, one input one output. However, for the same seesaw system, in some cases you could have only one state, or you could have 5 states, 10 states, and so on. So, the notion of seesaw really denotes how many inputs and outputs you have and not the number of states you have. Now, let us go back and then look at the liquid level system, and when we look at the equation from the last slide and the last lecture, you have equation of this form. And if you notice this equation, you will see if I want to write it in this form, I will say h hat dot, because I am taking a derivative of this, is sum A h hat, where this A, for example, can be this, plus B u, right, where this u is Fi hat and this B is this. So, you can also write this as Fi hat. Okay. So, now you notice the close similarity between this equation and this equation here. The only difference is that it is really not a difference. The thing that you have to note is that this number of states is 1 in this case, right. So, this matrix equation or a vector equation, if you want to think about it that way, becomes a scalar equation here. Okay. So, there is only one state and there is only one input Fi. So, if you think about this, then you can say the states h hat and the input is Fi hat. Now, what about the output? If we were solving a control problem where we are essentially measuring the height of the tank, and the output of interest that we want to control is really the height of the tank, then the output is also h hat. Okay. So, that is the mapping from this liquid tank example to state space example. So, I just want you to understand really that after a while we will simply be saying x dot equal to ax plus bu, but you want to understand that these parameters in this model equations are not abstract, they come from real physical system, and if you were to model liquid level tank problem as a state space model, you would simply write x dot is ax plus bu, but you have to remember that A is computed using this resistance, it is computed using the area of the tank, and also it is computed using the steady state of operation. So, these parameters themselves represent or reflect the process that you are trying to model. So, that is a very very important idea to keep, and you should not lose this connection, because as we go learning more and more about this, we will tend to abstract all of these concepts in terms of models, and after a while I do not want it to feel like it is pure math, whereas it is really not, because this A and B, you remember, if you have to solve a problem, have to be calculated, and those calculations will bring in the specificity in terms of the process that you are trying to model. So, after all of this, the state space model would be of this form here, because I said h hat is x, x dot is this times x plus this times u, and since h hat itself is output, y equal to x. So, there is only one output, and that turns out to be the one state that we have in this process, and this is a fixed number, because the resistance is a fixed number, area is a fixed number, and we know what steady state we operate at, and again this is a fixed number. So, this is an important thing to remember. Now, if you had more than one state and more than one input and output, then when we get these fixed numbers, we have to do more derivatives for different functions and so on, so that we can get a general nonlinear model into this form right here. So, if there are multiple functions, you have to do the derivative of that function with respect to the multiple states and so on. So, we will get back to that aspect of how do I convert a general multivariable nonlinear model into a linear state space model like this. Right now, we have a simple one state, one input, one output nonlinear model, which we have converted into a state space model. Now, let us do one more example to see how this works in a very very simple multivariate setting. To simplify this and not complicate this with derivatives and Taylor series and so on, you will notice that I will use a slightly different phenomenological model for characterizing a flow as a function of height. Again, this is an approximation. You could directly use this approximation, or you could write the other phenomenological model and linearize that model to get to this approximation. The quality of models will slightly vary, however, both are approximate. So, that is something that you want to remember. In most of this modeling, there is nothing called absolute truth, this is absolutely the true model, right. We will still talk about true process, that is our conceptualization of the true process. The true process, which is the real process, will always be abstracted out a little bit whenever you do modeling. So, that is something that is very important to remember. Now, just like what we described in the modeling exercise before, let us do that exercise here. So, here there are two tanks, and there is flow into one tank, and there is flow out of tank which goes into another tank, right. So, this is an example which is used quite often in all control textbooks, and this is called the example of non-interacting tanks. So, there are two tanks which do not interact with each other. Now, as before, let us start doing the variable definitions. So, I know that there is a height of the first tank, so that is a variable that will be of interest to me. I know that flow in, I have to define a variable. I know that for a flow out, I have to define a variable. So, if I define these variables for the first tank, it looks like I have enough variables that I need to write the model equations. I do a similar exercise for the second tank, and when I come here, I do notice that I already have a variable for the inlet. So, I have to only add two more, H2 and F3, which is the flow out of the tank. So, if you collect all of this, as of now I have 5 variables. So, like before, remember I need to look at enough equations for these variables. Then let us go back to the first tank and then see if I have to define any more parameters. We would define A1 as the area of this tank. Like last time, we could also define a density, but we know from the last exercise that the density cancels out if you assume the density is constant. So, to keep the algebra simple, I am not going to define a density. However, we know that for this valve we have to define some resistance. So, let me define a parameter resistance R1. Okay, so, these are two parameters for this tank, and similarly for this tank I will have two parameters A2 and R2. Now, I have 5 variables and I have 4 parameters. As I said before, these parameters are not calculated as part of the model, but they are given to the model. Now, let us take a close look at the 5 variables that we have for the process, and then if I draw a battery limit here, something like this, then I know the only input into this process is F1. So, there is no way in which I can compute F1 out of a model that I write. So, I am going to call F1 as an exogenous variable, and I am going to say if you do not give me the value of F1, I cannot solve these model equations. So, we will have to really look for only the 4 variables. F1 comes from outside the system. That leaves us with variables H1, F2, H2 and F3 that I need to have equations for, and clearly and logically. Last time we wrote one control volume, this time we do see that there are 2 control volumes which are independent of each other that I can write a balance for. Now, I mentioned that you could choose several different control volumes, and the model equations, though they are the same in many cases, will look slightly different. For example, in this case you could write balance for one tank and an overall balance for both the tanks. So, you could write a balance for tank 1 and an overall balance for tank 1 and 2 together. You could write a balance for tank 2 and an overall balance, or you could write a balance for tank 1 and tank 2. So, all of those will be similar, but nonetheless you cannot get more than 2 equations. So, for example, you cannot write a balance for tank 1, tank 2 and an overall balance, because the overall balance will simply be the sum of the other 2 balances. So, you can only write 2 equations. We have 4 variables still, but we know that we can use phenomenological models to get the extra equations. So, if I were to write a balance for tank 1, just like last time, this is the accumulation term. There is a rho W, remember, which is getting cancelled out. So, this is actually mass accumulation, not volume accumulation, just so that we say this scientifically correctly. Now, that will be input minus output. So, there will be rho W F1 minus rho W F2, and this simplifies to F1 minus F2. So, this is the mass balance for tank 1, which gives us our first equation. Similarly, you can write a mass balance for tank 2, which gives us our second equation. So, if you notice this, there are all the 5 variables that are participating in these 2 equations, H1, H2, F1, F2, F3, but clearly this we said has to be given to us for the model to work. So, we will not worry about that right now. So, the remaining 4 variables I have 2 equations. So, I have to look for 2 more equations, and clearly for each one of these valves you can write this phenomenological model that we have. Last time we wrote the flow across this as R times root H. We are going to simplify this and then say we are going to use a simpler approximation, a simpler phenomenological model, where the flow is related directly linearly. So, for example, for this flow across this valve F2, I am going to say it is simply R1 times H1, which is what is written here, and for the flow across this tank valve, I am going to say the flow rate F3 is R2 H2. Now, if you substitute these back into your equations, then you will get A1 dH1 by dt is F1, which is something that we need to be given. F2 from this phenomenological model is minus R1 H1. And for tank 2, you have A2 dH2 by dt is F2, which is R1 H1 minus F3, which is R2 H2. So, you have this equation. Now, what you can do is you can rearrange this equation, simply get some of these terms to the left hand side and you will get this equation. So, this is very simple algebra. In the first equation I have just moved R1 to this side, and in the second equation I have moved R to this side. Now, just to put this in a particular form, what I am going to do is I am going to define some constants, and I am going to start using these 2 constants tau and k, which is used quite a bit in control. Tau typically represents what is called a time constant, and k represents a gain, and we will see this more and more as we do control. So, this slide is very simple algebra, right. So, I am just going to show you the definitions and I am going to show you how these translate into state space model. What I suggest you guys do is simply look at this slide, start with the equation in the previous slide and basically go through this algebra and get to the final form, so that you are comfortable with how we do this. So, in this case, if you look at this, I define dH1 by dt as h1 dot, dH2 by dt as h2 dot, and I define two time constants tau p1 and tau p2, and basically I define kp1 and kp2 and do some algebra, and finally I will get this state space form. So, this is the important form. Now, notice that if you look at this as x dot equals ax plus bu, as we mentioned ax plus bu as we mentioned at the beginning of this lecture. If you notice, there are two states h1, h2. So, x dot is going to be a 2 by 1 vector, and that basically meant A has to be a 2 by 2 matrix, what we described last time, and you can see that this A is a 2 by 2 matrix, and there is only one input u, right. So, one input which is basically f1 or fi. Then basically the B matrix has to be of size 2 by 1, and you can see that this is a 2 by 1 matrix right here. So, that is how you have a multivariable state space model that comes about, which you see using a very simple example. Now, you might ask what happens to the output equation. So, the output equation depends on what you consider as output. Supposing you are interested in measuring both H1 and H2 and then controlling both H1 and H2, then the states are H1 and H2 and the output will also become H1 and H2. So, that will be two outputs. That means based on our notation P equals 2, that means you should have the C matrix also be of size 2 by 2. In this case, if your outputs are H1 and H2, so basically the equation you will write is H1 H2 equal to 1 0 0 1 H1 H2. So, this basically says H1 is H1, H2 is H2. So, whenever the states and the outputs are the same, then you will have an identity matrix for C, and in the previous slide I also had y equal to Cx plus du. In this case, because there is no effect of the flow directly on this, d equal to 0. So, that is how this state space model will look like. Now, this we cannot call it as a seesaw system because though there is only one input which is f1 or fi, there are two outputs h1 and h2. So, this is actually two outputs, one input system. Now, if it turns out that your interest for whatever reason is only in maintaining the level in tank 1, then H1 is your only output. So, in this case P equal to 1. So, the C matrix will have to be of size 1 by 2, right. So, when you write this H1, you will write this as 1 0 H1 H2 Cx, again plus du, since there is no effect of u here, d is 0. So, if you notice this, now H1 is H1 is the equation and C is 1 by 2. Now, for some reason, if your interest is in controlling H2 or the output is H2, then you will write H1 equal to 0 1 H1 H2, and similarly du, this is 0. Okay. Now, you notice that the C matrix differs slightly depending on what your output is. However, the difference between these two cases and the case where both H1 and H2 are outputs is that these two cases are seesaw cases, single input single output case, because the only output is H1 here and the input is again F1 or Fi, and the only output here is H2 and the input is F1. Okay. So, basically what this says in this example is I have a seesaw system, however, I have more than one state. In fact, in this case I have two states. So, this is how we convert a physical model into a state space model. In this case, by a choice of proper or relevant or phenomenological model that obviates the need for linearization, I was able to directly write this in the linear state space form. However, if I had chosen to model the flows as root of H1 and root of H2, then I would originally get a nonlinear state space model, and then I linearize that state space model and put it into this linear state space form. That might be a good exercise for you guys to attempt to see and understand how all of this works. So, with this I will conclude this lecture, and I will see you in the next lecture. Thank you.